Hello everyone. Today I will be talking about improving Linux for real-time workloads. I will start the presentation with some basic concepts on real-time, and then part 2 we'll be talking about things that are already in Linux that can and improve the real-time behavior of the operating system. And the part 3 is something that I'm currently working on, but I will say that whenever the time is ready. Well, the classic who am I slide. My name is Leonardo Braz Soares Passos. I work at Red Hat at Verteam. I do some work with Linux kernel. One of that is improving it for real time, which is this presentation about. I also work with some RISC-V code, ARC-specific code, but as a side quest. And I also do some improvements with live migration. That's my main job, to be honest. You can find me at my handle Leo Braz, at GitLab, GitHub, or at redhat.com, whenever you need to talk about something. Well, part 1, the basic stuff. I will introduce the basic of real-time and what is it. I can't just assume everybody knows that because it's not very used, very spread. Well, these are some definitions you can find at Wikipedia. Real-time is honestly, I like this one better. Real-time is about having a request or something like that and replying in a defined time limit. After you pass the time limit, bad things happen. So the idea is to try your best to stay at this time limit, which are called deadlines. Well, why does that matter? There are some workloads that need that. You need that your reply to a request happen in like some limited time. There are several consequences to that. If that fails, if you fail to reply on that deadline, there are systems that we call hard real-time. The idea is that missing a deadline is total system failure. I will have examples in the next slide. You have firm real-time, which means that you can have some infrequent losses of deadline, but that will deteriorate the performance, and those those answers to your requests will be useless, to be honest, after that time that deadline is reached. And you have soft real-time, which is basically you can miss some or a lot of those packages, those replies at time, and you will only degrade the performance, but that won't be like critical. Just to make sure everybody understands here, a deadline in real-time workloads is like this. You receive this request, this event, you do the workload and have a result or response, and this response time cannot surpass a deadline, a maximum value of time. That will depend on the workload. There are workloads that this is like a few milliseconds. There are workloads that means like nanoseconds or microseconds. So it will largely depend on the workload. Some few examples of hard real times. What don't you want to miss a reply on a system? Imagine that you have a pacemaker. You don't want that to fail on you. Imagine that you're having robot surgery on your heart. Missing a package or two may be fatal. Imagine that you have like this assembly line, and your sensor triggers something. That something is wrong at your assembly line, and you miss the time to actuate and remove that product or so. Maybe you have some catastrophic consequences, and you have to stop your assembly line, and that's terrible for like money. There are other examples of soft real-time, which means that missing a deadline is not that bad. Imagine that you're having some online meeting, and, well, if you can't just delay the replies for a long time, or else you are having this conversation and you speak something, and it takes for you like 3 or 4 seconds to the other part to listen. So that's one kind of a real time, which is really important. And well, Steam Deck, well, we were talking about Steam Deck earlier. Video games, imagine that you are like playing that game and you click your mouse and it takes like 3 seconds to do the shooting, and you lose the game, most probably. So that is some kind of thing that you have to have in mind, that you can't delay those kind of stuff because, well, it will degrade the perception and the quality of your service or product. Okay, if time is so sensitive, that means that you need to reply fast, and usually, historically at least, this kind of applications will run on top of bare metal systems, or meaning no operating system. And this is great because you can use the interruptions. You can use you can have some while loop running there, and it will get you very fast responses. But the thing is, and you, of course, you avoid the latency and like interruptions of the operating system. But well, programming some stuff like this may take a long time and may be very complex depending on your architecture. So, well, you can use an operating system. You have drivers, you have instructions, libraries. It's much easier to code on something that code your application on top of an operating system. So people created operating systems that are focused on real-time workloads like FreeRTOS, Zephyr, and RT-Linux. I will speak about some of them, some strategies they use. Because the whole idea is that you can't use a server-grade operating system to run these workloads, because those operating systems are focused on throughput. The amount of tasks that you run and not the time that you take to run them is more important, because, well, you have a lot of workloads. Processing them, taking a few more seconds, doesn't matter. You want to have a lot of output. And real time is not like that. You need to have latency. You have to deliver the task fast, even though you are like wasting resources on that. Well, Zephyr, for example, you have a simpler kernel, a lot of real-time oriented mechanisms like locks and queues. You have many schedulers available. And for different RT requirements, so you can opt for having more performance if your real-time behavior is not a hard real-time, for example. FreeRTOS, the whole OS is deterministic. You have a lot of allocation options, so also you can like have better performance and depending on your real-time requirements. RT-Linux is something very interesting. The idea is that you have a thread for running Linux, and it's kind of virtualized because it uses a virtualized interrupt control. I have an image on that. But the idea is that you have these real-time threads that run from RT-Linux, and everything else that's not RT are run on a thread that is like a guest VM with Linux running. Something like that. You have RT-Linux. This is a thread. The RT workload will run as a POSIX thread here from RT-Linux, which is not Linux, is a completely different operating system. And one thread is Linux, which is the usual Linux that have all the features and tools that we are used to, and the no-RT tasks run here. When you have an interruption, and it's an interruption for Linux, it will go into interruption handlers of the RT-Linux, and then to this virtualized interrupt control, which will go to Linux and then to your tasks. But when you have an RT-related interruption, it will just go to interrupt handlers and RT workload. So this way, you can just like schedule out the whole Linux operating system and just focus on your RT workload. It's a very interesting concept, but here you have the limitations of a very restricted kernel. It's not like programming Linux, okay? It's like programming on a much more, on a system with much less resources, much less tools. You can't use everything that you are using on Linux. Well, on that, what about Linux? Is Linux an RT operating system? No, it's not. It was planned for real-time, not for real-time, but for performance. It focuses on throughput instead of latency. You want to have a lot of things done. It doesn't matter how much it will take. So it makes a lot of sense for server workloads and have no deterministic behavior, meaning that you can have a loop, or it can take much more time on given system call on some situation and be really fast in other situation. And the workloads can and will be interrupted by the kernel or by other tests that for some reason need to run. So this will cause missing deadlines, which are bad. Remember, the whole idea here is that we don't want to miss deadlines because that's fatal. Well, but Linux is great. Everybody wants to program on Linux. It has a lot of tools, a lot of features, much easier to work with that than working with like bare metal. So, well, you can use practically any computer language, programming language that you want to use. You have libraries, you have tools, you have GDB, you have GCC. You have an extensive hardware support. I believe most of you have seen the Linux kernel code, and it's a lot of drivers there. You have a lot of options to choose from if you are a hardware vendor. You can assemble your solution with many hardwares and use the drivers that are already there. And you have the source. So if it does not fit your needs for some reason, you can just change it and use that like that. So the whole idea is how can we improve Linux to be more like a real-time operating system. The first step, which is already, the whole part 2 here is about things that are already in place at Linux. So everything that you see in part 2, you can already use its own mainstream.
Just a question
Sure.
Before we get into
Sure.
it. For how long have these been part of core Linux?
Some of them a long time, some of them are more recently being merged, like preempt RT is being a long time, but was not upstream Linux. Now it is. So it will depend on the feature. There are a lot of features.
Yeah, just to give you an idea, I think I talked about that at LinkedIn in one of my posts about your presentation. I mean, when I was at university, like 20 plus years ago, I was working with a set of patches from Politecnico di Torino that enabled real-time on Linux kernels. It was probably a completely different design from what we have today. I don't know much details about today. At that time, it was like they have, the scheduler had a separate high priority queue that basically you used to write kernel modules, and this high priority queue was scheduling these kernel modules with higher priority than the user space tasks. So that's the solution they provided at that time. So it was good because you had Linux, but at the same time you had to write kernel modules to run real time. Now, when I joined IBM back in 2006, IBM had a team dedicated to enable real time on Linux mainline. So this is not a new talk. I mean, this is something that has been happening for more than 20 years. The thing is that Linux is much more prevalent today than it used to be. As Leonardo said, I mean, everybody wants to use Linux because it's just easy, right? So that's why I think this has grew in importance in the past years.
Yeah, that's correct. Well, let's retake that. Your question is okay. the first thing here is scheduling. The scheduler needs to shift from a performance-oriented scheduler to from performance to a real-time oriented scheduler, and we have this. We have those are the ones that are usually used. They are performance-oriented, but they are also the sched FIFO, sched RR, sched deadline, which are real-time oriented. What is the idea of the real-time scheduler or real-time oriented schedulers? Is that they pick the task with the higher priority and don't let them go until they are finished. Okay, that's the whole idea. It varies though. It's somehow different between them. Sched FIFO and sched RR are basically the same when you have a single task in the higher priority level. The idea is that they will run that until it's finished. And sched deadline will seek this, will calculate with parameters that you pass about your task to decide which is the one that the deadline will finish sooner, and it will pick that, and until the deadline is over, it will work with that, and then switch to another task. Sched FIFO and sched RR, which is round robin, vary when you have multiple tasks on your higher priority level. So the idea is that sched FIFO will take the task and run it until it's over, and then switch to the next task. But the idea is that it will choose the task that was scheduled first. So that's why FIFO. If you schedule in time here, task A, then task B, then task C on the higher priority level, and you have on your lower priority level task D, task E, and task F, it doesn't matter the relation in time between those two. Since this is the higher priority level, it will do them first, in order in which they arrive at the processor. Sched round robin will take this limited time slot and will use those time slots to run parts of those tasks, and it will run here a part of task A, then a part of task B, then C, and then go back to task A, B, and C until they are finished. And then when those tasks are finished, it will go to the lower priority tasks and do that there. The sched deadline here, it will calculate which deadline will be due sooner, and we'll work on that before. Here you have this deadline will be finished before this and before those, and you have them in order here.
So
Sure.
in the previous slide, you said that the previous one, the sched deadline you have to provide some more information about the runtime and the deadline to the scheduler. So how do you calculate the runtime in this case? Because this can vary a lot depending on the architecture, the processor, and number of parameters. Yeah,
that's something that the person that is programming the real-time workload will be the possibility to provide if he wants to use this scheduler. It's kind of hard. Yeah. That's why we usually will use the sched FIFO, which is much easier and less interrupted. So.
Yeah.
Sure.
So going back on the same slide, this means that you can have a process sleeping with the lock.
Oh, sorry. This is after. Sorry. I will reach
No problem.
Sorry.
I was asking a question.
Oh, you went forward.
Yeah.
Okay.
I was asking a question about this one, but he go.
Sorry. I didn't see. Sorry. I will reach there. Please go on.
What's the difference between these scheduling policies and the ones from FreeRTOS, for example?
No idea. I'm not an expert on RTOS. I just presented them as another option. But the idea is that Linux is much more complex, so it deals with more stuff. So that's the idea.
So we have a specialist on Zephyr.
Just tracing stuff.
Okay.
Going on. Preempt RT, what is it? The idea is that you have this option which was quite recently merged in the kernel, like a couple of years, which enables you to make Linux a fully preempted kernel. What is the idea? What is preemption? The idea is that you can you can interrupt the kernel, which usually is not very useful to happen because programming a kernel which is interruptible is kind of hard or inefficient. But you can enable this and have your kernel to be preempted or interrupted, right? By user space code, if nothing else. So what does change it? It will replace the lock primitives, spin locks, read-write locks, etc. And you can have a sleeping spin lock, for example. They are preemptible, have priority inheritance. And with that changes, those changes that were proposed by Thomas Gleichner, I suppose that's how it's called, you can make the kernel mostly preemptible and break those long tasks that were previously not preemptible. It comes with a cost, of course, but you get like more real-time behavior on that. It can be enabled or disabled depending on whatever you're doing. So don't worry, like, will this be something bad for my workload? If you don't enable this, it's fine. You don't need to. It's just for real-time workloads. Well, of course, some parts like the scheduler can't be like preemptible, so or else you have a mess. So there are some pieces of code that can't be preemptible. And for some reason, okay. Why is kernel preemption good for real-time workloads? If you have a workload which is higher priority, it can stop the kernel. And if you can stop the kernel to do your workload, you can get CPU time before. And then you can like run that before and give the answer before, the reply, the result before previously. And that means that your deadline is less possibly being missed.
Okay. At the same time,
Yes.
you can maybe create some kind of denial of service in the kernel.
Yes.
Is there any protection against that?
I'm not that expert on that part, but the idea is that you can still be interrupted by some stuff on the kernel, some housekeeping stuff. And that's not like you will run this full % of the time. That's why there are some other changes that will improve that. But even though just for the idea of this presentation, we are still hitting some issues with that. I'll reach that, and it's more on the end of the presentation. The idea here is this is something without preempt RT, this is something with preempt RT, and you have a key user code, you have here user code, you have the scheduler, and you schedule some kernel code here, and this kernel code is interrupted by the, let's say you have this real-time request, which is an RQ, so for example, a sensor, a GPIO sensor, it will cause an interrupt, the kernel will deal with that, go back to work with the whatever it was working on, and then it will schedule it to your user code again. With preempt RT, you can, like, after this happens, you can schedule out your kernel code and do the user code, have the reply here for your request, your real-time request, and then you go back to kernel code here. So mostly you have higher priority than the kernel, so whenever you need to do something, it will happen faster. That's the whole idea here. Next feature that's interesting for real time is the CPU isolation. Well, what is it? It's a kernel boot parameter that removes the CPU from the list of CPUs which your scheduler can automatically assign work. So when you pass a given CPU to that parameter, you say, well, Linux, don't schedule anything automatically on here. And then after that, you need to schedule your tasks there manually, pin that to your CPU so they can run there. There are further options on this, which you can like disable tick, which is a timer interruption to check if there are any other tasks with higher priority to run on your CPU. But the whole idea here is that please focus on the CPU isolation thing, that don't let the CPU, the scheduler, to put any task on there. I have a mesh here so it's better to understand. What does it change? I've already gone through that. So you have less interruptions here because your CPU is not running like 5 tasks. It's just running 1 or 2 tasks that you manually assigned there. So there is a your real-time workload will have more CPU time and the processor fully available for it. So there are less interruptions, less scheduler interruptions, let's say. How does that improve the real-time behavior? You have the CPU all for yourself. There are less tasks running there, so you will, in the end of the day, have more CPU time, which means that you are less prone to miss a deadline. Here is a picture, so it's easier to understand. When you don't pass a ISO CPU parameter, in this example here, it has 4 CPUs, so scheduler knows that it can schedule work on 0, 1, 2, and 3. So here you have CPU 0 with a lot of tests, CPU 1, CPU 2, and CPU 3, and when you pin a task on CPU 3, it will like compete for CPU time with the other tasks that can be moved here. When you pass your isolate CPUs for this example 1 and 3, CPUs 1 and 3 are free. Scheduler won't automatically schedule anything here. So you have to manually ping a task here, and this task will run without any competition. So you are sure that you don't have anything else running on that CPU. The other feature is no hertz full. The idea is that you disable the tick, which is this interruption, this timer interruption that checks for different tasks that can be a higher priority, which makes sense on situations where you have an isolated CPU, for example, that there is nothing else running there. You don't need your scheduler to be from time to time interrupting your workload to check if there is something else to run, because you guarantee that there is nothing else running there. You can only enable that if you have this configuration here in the kernel. So it also offloads the RCU callbacks, but I won't get into details with that. Well, disable the check. So your workload won't be periodically interrupted. So less interruption to your workload. And this is nice to the RT behavior of your operating system, because you won't have those ticks happening and interrupting your RT workload. So there are less chains that you will receive a request and your CPU will just have this tick and the scheduler will run, and then you'll miss your deadline. Something like that. The scheduler, let's say this is the tick, periodically, and after some time it will try and check if there is any other tasks here. And let's say that you get a real-time request here, it will only process that after your scheduler finishes verifying, so you can have a higher total time, like this can be greater than your deadline. And with no hertz full here, you can just process it because there are no scheduler interruptions. That's the main improvement, let's say. Well, then this is part 3. This is something that will require some knowledge with kernel, or at least with locking primitives. I'm not sure how many of you will be able to, but I suppose all of you will. The idea is that we have an issue, which is what we are talking about, inter-process interruptions. Let's say that we want to clean the cache, for example, for all the CPUs, and we have a routine that needs that. that will still happen. We will still have these APIs that will interrupt the kernel. So it will interrupt your workload to happen. And those, will interrupt your RT workload. So all the problems that you may miss the deadline still happen here. We get a lot of those in the field, in production. So the whole idea here is to avoid those inter-process interruptions. The cache cleaning situation is not the usual situation because that needs to happen this way. But there are a lot of APIs that are not necessarily, they don't need to be an API, okay? Well, why this is a problem for real time? These APIs will schedule out your real-time workload and take time, and we don't want that. So you have an inter-process interruption here. It will have a context switch. You run your API, and then you have another context switch. So let's suppose that you have your real-time request here. It will take this much time to process that. It could take like just this much time if you don't have this API here. But of course, some of them are not non-negotiable. This is hard to solve. Like, we can't just remove all the APIs, as I was saying, because that will be very bad for the kernel. There are very efficient parallel programming algorithms that use API. Basically, they use local locks, and local locks are just for your local CPU. In many situations, it will just like disable preemption. For real time, you will just get a spin lock, which is local, so it's very fast. And then you just use the API very not oftenly. So it's a high price to pay, but overall it's very efficient. But it's not good for real time because those APIs are bad for real time. So there are a lot of APIs around the kernel because of those highly efficient parallel programming methods. And each case of those APIs, each case we have to use to remove these APIs will require a lot of study. You can't just like remove all of them and have your maintainer to think that it's okay to do that. It will touch very important code like memory management code or C group code, which is stable for a long time, and we can't just like remove or change that in a batch, okay? So there is no general API replacement solution. Every solution of them will take time and will take resources. And will take a lot of conversation with your maintainer because some of them are perceived as drastic changes. And you will find a resistance from the maintainers. And of course, it's their job. So the whole idea is, if it takes a long time and each case is really important and it requires a lot of work, how can we decide which API is the most important to remove first? For this, I propose the solution of a trace point, which you can enable, and whenever you miss a deadline on your code, you can get the logs from the tracing. And with that, you can see and you can check which APIs are bothering your real-time workload. And it's very specific because it will depend on the other things that are running on your processor. So you can use that. The idea is that they are called CSD function entry and function exit. So in our scenarios, we enable everything, no heartful, scad FIFO, and preempt RT, isolate the CPU, and then you keep track of your deadline. You can like put a debug on your real-time workload, and whenever it misses a deadline, you get the log, and you compare it with your times and see what was running, which APIs were running during your time slot for your real-time request. So you will see something like that in the end. You have this real-time request, you have entry and exit of a few APIs, and you have your last time here for your deadline failing. and you can see, well, this is something that is bothering my my workload, but this one here is bothering it more. So I can try to deal with that first. That's the strategy that we are currently using to determine which API we can remove first. What else I'm working on? Well, removing these APIs. There are some low-hanging fruits there. There are some algorithms there that use all the processors to distribute some workload. For example, pcrypt. Encryption can be expensive, so pcrypt will give for each processor that is online on your machine, it will give it some work to do, part of the encryption work to do, and that's great. But if you have an isolated CPU, you probably don't want that. So in this case, the change is really simple. You just say to your algorithm, well, if it's an isolated CPU, don't schedule work there. And that's basically why I have proposed it here. The idea is that you get this housekeeping CPU mask, which will say, well, these CPUs can do work queue stuff. And this CPU mask is basically a integer, which have 1 bit for each of your CPUs, and we'll just have a 1 if the CPU is able to do like work queue stuff, and a 0 if it is not able to. So the patch here is simple. I just get this CPU mask and I do an AND operation, logical AND operation, with the online mask, and I only schedule stuff there. So basically what I'm saying to the algorithm is, it's isolated, don't do pcrypt work here. There are this, I saw this at least in 3 very important points in the operating system, in the base operating system, which they use local lock, schedule work on, and we can replace them with spin locks. But wait, spin locks are locks are expensive, right? So the whole idea of using local locks and schedule work on is to avoid having locks in your hot path, okay? So why am I trying to replace them with spin locks, which are in this case expensive? The whole idea is that if you can have a spin lock that is you only get this lock, or you mainly get this lock on your local CPU, like a per CPU spin lock, you don't pay a huge price. You pay like 12 clocks for my experience, or down to even 5 clocks, if clock cycles in this case, for getting a spin lock. So it's not that expensive to replace a local lock with a spin lock. Of course, it's a cost. It's some few cycles. If you run that a lot of times, you will pay some price. But with that, you can remove this API. So it's useful for real-time workloads. How does that work? The idea of spin lock is to avoid parallel execution, like you sequentialize it, so you don't access memory with 2 processes at the same time. And the same strategy is valid for local locks, okay? When you schedule work on a remote CPU, you just say to that CPU, run this locally, and the local locks still work fine. So with spin locks here, you, instead of like interrupting your remote CPU to do something, and those some cases are just in software cache, for example, you can just like get this spin lock remotely and just do the work and don't interrupt that CPU. It's not that expensive. Schedule work on picks at least 1 global lock and a local lock, so it's much cheaper to do this part of schedule work on. The thing is that this is not run as oftenly as the local lock part, so there is some price to pay. My argument is that this price is not that big, so it's worth to do that if you are running a real-time workload. That's how it should be looking like. Just a minute. That's how it should look like. You have, currently in the kernel, you have this local lock here. You do the local work and then lock on lock. And when you have a remote CPU, which you work to do some work on, you have to do some work on, you just schedule work on that CPU, and that's it. And what will this trigger? It will trigger an API, and the remote CPU will get this work queue and do the work there. This is what I'm proposing. You get a spin lock instead of a local lock, do the local work, and then spin a lock. This is the local work. And if you are doing a remote work, for example, you get that per CPU struct, and then spin, lock it, spin, do the work, and spin, unlock it. So it works great instead of a scheduled work. Okay, this can be done, and it's really interesting that, to be honest, I found out that real-time, the preempt-RT kernel already uses spin locks instead of local locks because it can't disable preemption at will. So it's a low-hanging fruit. You already get a spin lock every time in preempt-RT kernels. So there should be no issue if you just get the spin lock. I mean, you're already getting the spin lock on the hot path, which is the higher price to pay. So there is no issue if you just get the remote spin lock and do that. And today, as we are talking, the upstream kernel will get the spin lock, which is expensive, and then schedule work on, which is both much more expensive and will be bad for our real-time workload. So what I'm trying to do upstream today is to convince people to just get, it is already getting the CPU, the per CPU spin lock, so please go on.
Yeah, don't you create a scalability issue on the non-RT kernels when you replace the local lock with the spin lock on the hot path?
Sorry, can you repeat the question?
So on non-RT kernels,
Yes.
right, when you replace the local lock
Yes.
on the hot path
Yes.
with the spin lock, you create a scalability problem.
Scalability.
Yeah, scalability.
Well, it's a local spin lock. So that spin lock will only be at your local CPU, and it will only mostly be gotten in your local CPU. So the cache line is there. So it's a local cache line. You don't usually have this remote CPU touching your cache line. Okay?
So it's a per CPU.
It's a per CPU spin lock, of course, because if it's a global spin lock, then it's all in the trash here. Okay? It's okay.
Yeah, that's good.
Okay. The idea here is that the preempt-RT kernel already has a local spin lock, which it gets for doing instead of the local lock, and it's still doing scheduled work on, which is known to be bad for real-time kernels. So I'm proposing an interface in which, if you are using a real-time kernel, instead of doing scheduled work on, it will just grab the remote spin lock and that's it. In this case, if you schedule work on something, you're already touching the cache line. So it's a win-win situation. You're just not having to do a very hurtful work for your real-time workload. And that's it. It was faster than I expected, but do you guys have some questions?
I have a question. I mean, when we are doing virtualization, it's a little bit different. I mean, just something that I crossed my mind. I mean, when we are doing live migration, for instance, and if the live migration takes some time, the kernel complains a lot about being stalled, right? You have RCU stalls, you have block device stalls. You can have a bunch of error or warning messages saying that things are just not working. Does that happen with RT kernels? Because I mean, you are disabling the timer tick, you are disabling the RCU stuff, you are disabling the scheduler. I mean, doesn't the kernel complains about that?
That's the good thing about it. You are enabling all those stuff, but they are enabled per CPU. So let's say that you want to do a live migration or something like that. You can do that on the other CPUs that are not isolated. They don't have the check disabled.
Yeah, I mean, but I'm not not even thinking about live migration. I mean, I'm thinking about the regular stuff that is running, because I mean, even though you have a CPU that is isolated for the real-time tasks, there is still other stuff that the kernel probably wants to run there, right? So
Yes.
doesn't this other stuff complain about not being able to run?
That's the thing. Those things will be running there. You can't, at the current state, we can't just say that no API will be running on the isolated CPU with all those options. So that kind of stuff is the kind of stuff that we can't remove. All we can do about this is try to make it as fast as possible, so it won't bother the. So the whole idea is that we want the kernel to still working. I understand that if we just say, well, you won't be running any API here, the other CPUs will get stuck, and the kernel will complain.
Yep.
So there are stuff that we can avoid, just like this example where you are only touching software. So you can avoid these APIs, but there are APIs that can't be avoided. So all we can do is try to make it faster.
Okay, thank you.
Go on.
So I'm just, when you're talking about the CPU isolation, just came up to me. How do you handle thermals in real-time system? So like, imagine you're running the same task in a processor. It will heat up, and you might get a CPU throttle. And related question is, I remember reading that the kernel had some code to schedule tasks to average the thermal down, and I imagine for real-time systems this is not great. Right?
Yes, that's correct.
So how is there any smart way of handling that in real-time OSs?
Well, I can't say for every real time, but I know that when you are running a real-time workload, it's mostly a workload that will do some work and that will go idle. That's why we have to say that this task, well, don't schedule it out. It's idle, but we want it to be ready to respond for any request that comes. So the idea is that the other CPUs will run just fine. Linux has this balancing for thermal and stuff. But the isolated CPU, as it will mostly be idle and do some workload there and just stop for a while, I don't see, at least in field, any thermal problem there. And no throttling, because, well, it will throttle if you have a lot of workload in there, right? Does that make sense?
Yeah.
Okay.
So you just schedule small critical paths to the CPU that's isolated.
Sorry?
So you just have to schedule small tasks.
Yeah, real-time workloads are not usually very time-consuming, but let's say that you have a lot of requests and it hits some. Then you have some deadlines missed probably because of the throttling, but that's part of the specification. You can't just a lot of requests. You have to project your system to respond for a limited amount of real-time requests, or else, well, we have limited CPU time. You can't in any way, in any real-time OS, you can't just overload it with requests and expect it to fulfill the real-time requirements, okay? That makes sense?
Yeah.
Yeah, and usually you have requirements on your system about what to do if you start to miss deadlines, right? I think your other question was, what does the system do, right, if you start to miss deadlines? I mean, I think that depends on what you are running and what your requirements are. So just to give you an example, when I was working with real-time kernels, as I said, no more than 20 years ago, that was because there is the CTI, the research center here in Campinas. They used to have a project with an airship, mini Zeppelin, that was autonomous, and we had an operating system that usually that was a robotic airship, so it has some vision, and basically it could fly alone, right, by itself. So one of the requirements that we had was that it should be a real-time system, because as it was driving the airship, there are deadlines about actions that you need to take, and if we missed one deadline at that time, there was a watchdog that basically rebooted the system, right? I mean, as it was an airship, I mean, it would not fall, right?
This is not running an airplane.
Well, yeah, I'll get there. So, as I said, I mean, an airship will not fall if you just have to reboot. However, there were like requirements, and I was the one building the operating system at that time, so I know this in quite detail. The requirement that I had at that time was that the reboot could not take more than 10 seconds to have the user space up and running with the real-time tasks, right? Because even though it would not fall, it would, for instance, diverge from its route, right? On an airplane, it's much stricter probably. First of all, they have more than one system running at the same time and they compare the results, right? So if one of them starts to fail, they can just probably drop it and change to the other, right? They have some backups for this kind of stuff. So it depends on your requirements and this will drive what you need to do.
Yeah, sorry, another question. So I think, so maybe CPU boost is not a great thing for real-time systems, right? Like you increase the frequency momentarily for a CPU, and you get the CPU to run faster, but you also get it to heat up more.
Yeah.
And so do you guys like disable like CPU
You can
boost?
do that. You can use the CPU burst whenever like you have a lot of requests, but usually it does not happen because it's well specified, and the idea is that you can disable it if you want. But well, maybe you have some burst and you want to use it. But the idea is that the workload is dimensioned, so your CPU won't get a lot of requests.
Again, I think it depends on your requirements, right? I mean,
Of course.
just to give you another example from another area. So on cloud environments, usually you have Intel and AMD processors, and they have frequency throttling depending on the workloads that you're running. On cloud environments, this is not very interesting because the cloud provider does not want to provide you more CPU time than you paid for, right? And at the same time, I mean, you don't want the CPU to be slower than what you paid for as well, right? So varying performance in a cloud environment is usually not a good thing. And on the other side, I mean, cloud providers are not particularly interested in energy consumption at that level. Of course, they have the environmental concerns with the data center and using less energy, but not on that level. So if you get, for instance, Ampere, and I think Guilherme mentioned Ampere before. So Ampere is chip producer for ARM servers, right? And one of their pitches is that the Ampere processor that they are selling to Azure and to Google Cloud, it doesn't have variable frequency. It always runs at the same maximum frequency that the processor is capable because they want to have predictable performance on the cloud. So maybe for real-time systems, what you want is really predictable performance because predictability is more important than throughput in this case, right? So you probably want to disable frequency scaling, thermal control, all these things.
Yeah, that will majorly depend on the workload, right?
Exactly.
Yeah, the whole idea of like improving Linux is also for cloud. Clouds want to provide real-time able processors, so because they can get this share of the market, so it's interesting to have Linux doing that. And sure, go on.
So you mentioned that you cannot avoid APIs,
Right.
right? So they are not maskable.
They are maskable, but when I say that you can't avoid APIs, is that there are some algorithms that deal mostly with hardware that you can't just avoid them. Let's say, get this example of like you have a TLB cache that you want for some reason to clean. You can't just like say, well, I won't do that because I don't wanna. The other CPU will be hanging, waiting for you to finish that, and the CPU, you'll send the response, and then after all the other CPUs like do this cleaning, it will proceed. So you get your CPU stuck. So you have to answer that. Even if we can, for example, speed up that or give some like deterministic time for that to happen on like a time at which the workload is sleeping for some reason, you can do that, you can improve that, but you can't avoid to do that on unlimited time, or else your other CPU will get stuck. That's the thing that Leonardo Garcia was talking about also. That makes sense?
Makes sense, but I'm considering what do we do with NMIs?
NMIs, non-maskable interrupts. There are non-maskable. You can avoid them. You can try to remove the source of them on the isolated CPUs, but you can't just like say that they won't happen. Sometimes they will happen, and that's a constraint. The idea is try to make them as fast as possible. That makes sense? Some other questions?
Thank you very much, Leonardo.
Thank you, guys. You want to use them?
Yes. We will be back at 4:30.
Okay.